Hello and welcome to the first lecture video. As I announced in my very first video on the general information, I will present chapter 1 that gives you an overview over industrial scale production of polymers. So first I would like to tell you what we need to do in order to produce polymers on an industrial scale. I explained this outline, so this introduction will just give you a brief summary and motivate why we'll take the next steps. That means in chapter 2, we will look at the kinetics of polymerization reactions, and then later on, we collect more physical data, and finally, we use all these data in the scale up procedure for a polymerization reaction that we do in this lecture at the example of a stirred tank reactor. And yeah, with this short repetition of the general outline of this course, I will go into this general introduction in order to explain to you why we do all these things. So if we look at all the polymeric materials that are available, we have to distinguish between three different types of polymers. On the one hand, there is a big group that is called thermoplastic materials. And you all know these materials. Polyethylene is an important product from this group, polypropylene, polyvinyl chloride that we know for many applications in construction materials. So many things in our houses are made from polyvinyl chloride, for example, floors, or polystyrene or polyethylene terephthalate are also big industrial products that we all know, all handle every day. Sometimes we do not even know that we have such materials in hand, which, for example, polyethylene terephthalate is a material that most of our drinking bottles are produced from. The second important group are so-called thermostats. Thermostats are not that well known, or we do not realize what material we have in hand. So polyurethanes are the most popular materials. Mattresses, shoes, many parts in cars are produced from polyurethane, but also phenol, formaldehyde resins, or urea-based resins are so-called thermostats. And finally, we have the third group, the elastomers, that are elastic polymers, often made from copolymerizations. That means we need more than one monomer to produce them. Often we need a combination of styrene or butadiene. So we have multiply unsaturated monomers to build these polymers, or polybutadiene itself is a typical example with elastomer properties. So here we see again the typical properties. So the thermoplastic polymers have molecular weight of more than 100,000 grams per mole. The molecules are linear or slightly branched, and as their name says, they are thermoplastic. That means we can melt them, bring them into the shape that we would use later on for the product, and then we cool them down and solidify the material in the desired shape. The thermosets are materials with extremely high molecular weight, and they are highly cross-linked. So we cannot even give a molecular weight for these materials, so they are far beyond some millions of grams per mole. And what is most important is we cannot melt them. So if we heat them up, we destroy them. So we get thermal decomposition, but we do not get the monomer, but we just destroy them. And finally, we come to the elastomers that are again linear or weakly branched materials, and their most important properties is their flexibility. And most of them carry double bonds in order to cross-link them in order to form rubbers. So the elastomers are first highly flexible materials, and the final products that we would like to use need an additional step in manufacturing by cross-linking. So we can first bring them into the desired shape, for example, a tire for a car, And once we have formed them to a tire, we add some chemicals that do the cross-linking, and then we heat them up or do some other chemical treatment and cross-link them to fix the final shape of the product. If we now look at the market shares, we see that about 70% of all polymeric materials that are produced are thermoplastic polymers. Although we do not really realize that such a big share of polymer materials are thermoplastic materials, we have the impression that the other materials are much more present, like thermostats we have in many everyday products, or elastomers in tires and other uh, products are so present for us, but they have a much longer lifetime. For that reason, we experience them to be present in a much higher quantity. But the thermoplastic polymers, they usually have a very short lifetime. We use them for packaging and many other short time applications. And that's the simple reason why such huge quantities of these materials are produced, used for a short time, and then unfortunately deposited. And many of these materials end up in the oceans where they should not arrive. So we should use our knowledge about polymeric materials and change the situation by producing better degradable polymeric materials. So we should not skip the production of such products, but we should change their properties so that we can carry on with their use. But if we synthesize them in a way that they cannot cause environmental problems, we can further on use their advantages and their nice properties that we all enjoy in our everyday life. Here we see a very simple plot, although based on the year 2004, but these numbers still change in the same way. So we have a strong increase in the production of polymeric materials. So worldwide, there's an annual growth of almost 6%. In Europe, it's around 4%, and especially in Germany, we have 17 million tons of polymers produced every year, and every year about 4% of these materials produce more. And that is a reason why we need to have a good knowledge of the production of these materials. These are large quantities of rather cheap materials. So the production processes have to be optimized. So these materials are not only sold because they are so great and they outperform everything else. The most important reason for the application of polymers is that they are rather cheap. So in many applications, the appliers look for cheap materials, and in order to produce larger and larger amounts of these materials to very low prices, we should design really optimal processes that require the smallest amount of resources, that means of monomers, of energy, and everything, investment costs. And this is only possible if we design processes at the best possible knowledge that we have about the progress of such reactions and their dependency on the process conditions. And we develop new polymeric materials every few years. So nowadays, many materials are produced from renewable resources, so-called platform chemicals. And also for that reason, we need a good knowledge about the design of industrial scale polymerization processes. Although we have a variety of polymeric materials in the market, the way how they are produced are not so different. So many of these materials are produced by so-called chain-wise polymerizations. That means the monomer units are added to a growing chain step by step. So one monomer unit after the other reacts in the polymer growth reaction with an active site that we introduce to the reaction mixture, and then this active site lines up one monomer unit after the others and allows the polymer chain to grow. And these active sites can either be free radicals or organometallics or even ions can act as initiator or catalyst for such polymerization reaction. And it doesn't make a big difference which way of initiation we use for the polymerization reaction. The propagation step that produces the macromolecules is in most of these cases exactly the same. So for that reason, the specific name of the polymerization reaction that produces the macromolecule can either be a free radical polymerization, where we initiate the growth of the macromolecule by the addition of initiators that decompose to free radicals. Or we can use catalysts, usually transition metal complexes, in a so-called coordination polymerization, because these catalysts have free active sites where olefins can be coordinated as an additional ligand, and then one monomer unit after the others joins this complex and forms a macromolecule. And a third way of initiating a reaction is a so-called living polymerization that is often done by ionic species that initiate the first step of the reaction, and then an active site is generated that is able to line up a huge number of monomer units to a macromolecule. In most of these cases, the lifetime of the active sites that carry the reaction is rather short. So the radicals in a free radical polymerization just lives for fractions of a second. But within this short period of time, this active site is able to line up hundreds or even thousands of monomer units to produce the macromolecule. If we now look at the other type of reaction that is called stepwise reactions, there we have monomers that carry functional groups that react with each other. So the best known example is a dicarbonic acid that reacts with a dialcohol. And acid and alcohol can produce an ester, and as long both monomer units carry two functional groups, they can produce chains, but they do not align these chains by starting from one side and adding one monomer to the other. They more produce first oligomers, and then these oligomers join to create medium chain length molecules, so let's say even bigger oligomers, and only at the very end of the reaction these oligomers join to produce the macromolecules. So here the active sites are the functional groups of all the monomers that we add to our reaction mixture. Very typical examples are polycondensation reactions of, let's say, acids and alcohols, or amines and acids that produce the polyamides. And in these cases, all the functional groups have to react one after the other. They have a rather long lifetime. So some of these active sites live for the whole duration of the reaction. And for that reason, we see quite a difference in the concentration of the active sites in these two different groups of polymerization reactions. So while the active sites in the chain-wise polymerization are short-lived time, their concentration is also rather low. So we have a really low concentration of free radicals or ions in a living polymerization, while in a stepwise polymerization, the monomer concentration, that means the active site concentration, is high at the beginning, and during the polymerization, this concentration decreases. In these stepwise reactions, there is essentially the propagation step. That means the step that causes the growth of the macromolecular chain. In the other type of reactions, we have a combination of elementary steps. So we have initiation reactions in the free radical polymerization, coordination polymerization, also living polymerization. We have the propagation reaction that has to happen in every polymerization reaction, otherwise we will not obtain macromolecules. And then we have termination reaction that stop the growth of an individual macromolecular chain. And sometimes we even have transfer reactions. There, the active site is transferred to another species and the reaction carries on then at a different molecule until again a termination reaction happens and a stable molecule is formed that cannot further react. This means that the molecular weight in our different processes develop in a very different way. So in the chain-wise polymerization, we produce macromolecules right in the first moment. So even after a minute or a few seconds in a free radical polymerization, we observe the formation of complete macromolecules. While in stepwise reactions like polyaddition or polycondensation reaction, the molecular weight increases with time, and only at the very end we produce the desired polymers with the properties that are needed for their final application. And this development of the concentration of the species and the molecular weight with time has a consequence for the polymer concentration. So for living polymerization, it is constant all the time. During a living polymerization, a few chains grow and grow until we terminate the reaction. But for free radical polymerization and coordination polymerization, the concentration of polymer chains increase with increasing reaction time. So we produce more and more macromolecules. So we have macromolecules already at the very beginning of the reactions, and then we produce more and more of these macromolecules during the reaction. In a stepwise polymerization, the situation is different. There, the concentration of molecules decreases because we join more and more short-chained oligomers to long chains. So in the end, we have the lowest concentration of macromolecular species. So the highest concentration of species at all is present at the very beginning, because then we have the concentration of the monomers, and in the very end, we have a rather low concentration of macromolecules, and only once we approach the end of the reaction, we have the lowest concentration of macromolecules with the highest molecular weight. But it's not only a difference in the mechanism of polymerization reactions, we can also perform them in very different modes. We can apply very different methods. So what you all know from the laboratory is the solution polymerization. There you dissolve your monomers, your initiator, in a solvent that takes up all components. Then we heat it up, or we start it by adding the initiator, and we obtain a polymer that is soluble in the same solvent, and after a while we have a highly viscous polymer solution. So this is usually a homogeneous system. That's the reason why it's named solution polymerization, because we have a solution from the beginning to the end of such a polymerization reaction. In some cases, we even avoid the use of a solvent. We add the initiator just to the monomer. This method of polymerization is named a bulk polymerization, because we just convert a monomer into a polymer. This is done by the addition of an initiator to the monomer, and this can either be homogeneous if the polymer is soluble in its own monomer, or it can be heterogeneous. That means two phases form during the reaction if the polymer is not soluble in its own monomer. This is a very simple method to produce macromolecular materials, but it is a reaction mode that is very difficult to handle because you convert a liquid into a solid. That means the viscosity of such a reaction mixture increases dramatically. We will see that later. It's an increase by about 8 orders of magnitude. So it is difficult to handle this. Heat removal, stirring, many things can cause problems in this method of polymerization that looks first very simple, but if you want to scale that up and use that method in an industrial scale, it becomes a very sophisticated method. For that reason, we use solvents wherever it is possible just to facilitate the polymerization reaction. So if we do not use a solvent that dissolves everything, but a solvent that is just present in order to disperse the monomer and the other components, we talk about a so-called suspension polymerization. There we have a liquid and the monomer is dispersed in this liquid. So most monomers are liquid themselves. So we form a two-phase system. Usually the solvent in a suspension polymerization is water, and if organic monomers are dispersed in water, we obtain an emulsion, and if this emulsion is then initiated by the addition of a water-soluble initiator, the polymerization starts inside the monomer droplets and produces polymer particles. So inside these droplets, almost the same happens than I described before for the bulk polymerization, but now these monomer droplets are dispersed in water, and as long as they do not stick together, we produce polymer particles that are much easier to handle than one big block of polymer inside a reactor. Sometimes we add a little bit of surfactant in order to stabilize the suspension and to keep the polymer particles separated from each other. In this case, we name the method a suspension polymerization. And the big difference between this method and the next method is that here we add an initiator that is soluble in the monomer, or we just say oil soluble. So a hydrophobic initiator is added to the reaction mixture. It enters the monomer droplets and converts the monomer droplets into polymer particles. The next method looks very similar, but there's a substantial difference. Again, we use water as the solvent. We use monomers that are not soluble in water. So we have again a two-phase system. With strong stirring, these two phases are dispersed to produce an emulsion. And now we add a little more surfactant. So on the one hand, this surfactant stabilizes the monomer droplets, and on the other hand, it forms micelles inside the aqueous phase. And now we add a water-soluble initiator, and this water-soluble initiator enters these micelles. And now the polymerization starts inside the micelles, and very small polymer particles grow inside the micelles, let the micelles swell, and in the end, we produce something that we name a latex. So these latex particles are much smaller than the polymer particles that we produce in a suspension polymerization, and for many applications, for example for coating, we use these latex particles directly from the polymerization process. So little differences, but these methods allow us to produce very different polymers with very different properties, even if we use the same monomer. So you could do all these methods of polymerization with one and the same monomer, but you would not produce exactly the same polymer. So if you take styrene for a solution polymerization, for bulk, suspension, or emulsion polymerization, you would produce very different polystyrenes that can be used in very different applications. So the selection of the polymerization method is also a tool to generate very different products for different applications. If we now go further down in our list, we find even more methods like the slurry polymerization. That is usually polymerization where we have three phases. Again, a liquid where the polymerization takes place, a gas that delivers the monomer to the reactor, and a solid phase, that is the polymer that precipitates from the reaction mixture. This is a method that is mainly used for converting the gaseous monomers like ethylene and propylene. Other monomers are liquid under typical reaction conditions. There we do not need to apply these three-phase conditions. The most advanced methods, and it looks to be the simplest, but it is not. It's a sophisticated method. It's a gas phase polymerization that converts monomers from the gas phase directly into solid polymers without the application of any solvent. So, and if you use no solvent in the process, you don't have to remove it in the end. But it is very difficult to fluidize the catalyst and the polymer particles in a way that you can contact them with the monomer from the gas phase in order to let the polymer particles grow, and then you have continuously to remove the growing polymer particles from such a reactor. And only if that all works simultaneously, you're able to produce polymeric materials without any solvent, without any need to separate something, to purify something at the end of the reaction. You convert your monomers directly into a polymer that is almost ready for use. And the last method in this list is a precipitation polymerization that you might already know from your lab scale experiments. If the polymer that you produce in your polymerization reaction is not soluble in the liquid, it will precipitate. That facilitates the separation. So obviously, if it precipitates on its own, you don't need to evaporate the monomer or the solvent at the end of the reaction. You can just filter the ready-made polymer off and dry it, and then you can further process the polymer. So we have a variety of different methods available for the production of polymers, and as I said before, if we apply these different methods to the same monomer, we can produce polymers with very different properties, useful for very different applications. But this is not the only difference that can be used to produce polymeric materials with different properties. Also, the equipment that is used for the production of the polymers makes a difference in the final product and in the final properties. So the big brother of our lab scale reaction flask is a stir tank reactor. But that is by far not the only equipment that is used in industrial scale polymer production. We also know so-called loop reactors or fluidized bed reactors. And there is another group that is somewhat different from the stirred tank reactor. That is this group shown in the lower part of the diagram. There we have either tubular reactor or tubes that are installed in a vertical position. We name it tower reactors, or sometimes we even use extruders as reactors for polymerization reaction. And we make this difference of these two groups that is illustrated here because the stirred tank reactor, the loop reactor, and the fluidized bed reactor have about the same residence time distribution behavior. Because if we use a stirred tank reactor for continuously operated polymerization reaction, most molecules will only stay for a few seconds inside a reactor, and then we wash the reaction mixture out of these reactors. That means there is an exponential decay in the probability for the molecules to stay inside these reactors. And although these three reactors shown here in the upper part of the slide, although they look so different, their residence time distribution is very similar. It follows this exponential decay. For the other group shown in the lower part of the slide, we find something completely different, but again similar within this family of reactors. We find a very narrow probability function that describes the probability for the reaction mixture to stay inside a reactor. So we call this plug flow tube behavior. So we have a long period of time where no molecules leave the reactor, and then a very sharp peak that shows how most volume elements leave the reactor, and they all leave the reactor more or less at the same time. So for some reactions, it is very important that all monomers have the same time and the same probability to take part in the reactions. So this is especially true for polycondensation reactions or for polyaddition reactions. So there we have to apply these tubular reactors, while for other reactions where the active sites are really short-living species, it doesn't make a big difference how long they stay inside a reactor. They produce their macromolecule anyway within a few seconds, and this short period of time is available no matter what the residence time distribution inside such a reactor is. And this is true for the free radical polymerization or for ionic polymerizations. There we can apply these stir tank reactors or fluidized bed reactors for these reactions, and this is done in the case of the fluidized bed reactor for the gas phase polymerization of ethylene and propylene. The continuously stirred tank reactors are used for a variety of free radical polymerizations, again of ethylene, but also styrene, butadiene, and loop reactors are used for polymerization reactions that are operated at very high concentrations, because at high concentration we also produce a high heat flux, and from such a loop reactor a lot of heat can be removed from each single volume elements of such a reactor. So this is optimized for the cooling conditions of such a reactor, while the tubular reactors are more used for the condensation and addition reactions. So this is a very short overview. And in this little list of general references, you can read and learn more about the aspects that I showed and explained here. So we need to know about the reaction itself. We need to know how the reaction responds to a different reaction medium, as I showed it here in this table of polymerization methods. So we have different concentrations of monomers and initiators if we use different methods of a polymerization reaction, but also the chosen reactor has influence on the concentration profile of monomer as well as initiator and catalyst. And we have to know how the progress of the reaction responds to different concentration profiles in such reactors in order to design or first select such a reactor and then design it for a particular reaction, and in the end to predict the performance of such a reactor. And these things are summarized in these references. These are very general references, so not just from very current literature, but these basic things have not changed over the last years. So for that reason, I have chosen a number of very basic references to introduce you to this topic. And if you have questions, I will answer these questions in our lecture, in our online lecture then on Monday, the 20th of April. So please read the lecture notes. There you will find the information of this lecture again on the pages 1 to 4. The figures are also given in the lecture notes. And yeah, if you have more questions, I will be happy to answer your questions then on Monday, the 20th of April, and I will circulate the link for our online meeting on the ISIS platform. So see you in our online meeting. I'm looking forward to see you and answer your questions. Thank you for your attention.